Sounds good. So yes, I would like to talk about exciting future opportunity and some of the challenges that is happening at the crossroads of cosmology and galaxy astrophysics, very much in the spirit of 1984 discussion. We heard a lot about development in cosmology, and galaxy formation took place at the same time. And I think the field of galaxy halo connection has been very powerful. I think there's a new opportunity for us to actually study the gas distribution, diffuse gas, in the cosmic ecosystems, which is about to be disclosed. And we can actually, over the next several years, I think there's a real opportunity for us to be able to map out most of the baryons. In fact, we're transitioning quickly from census of missing baryons into precision modeling of cosmic gas profiling. And I think the reason is that there are a number of multi-wavelengths observations which will be able to map out in X-ray band CMB as a backlight using thermal and kinetic SZ effect, which is independent of redshift, as well as the new observation from FRB, which is coming online, and if their detection rate is growing exponentially. And all of this, of course, builds on the legacy of HST cost absorption line study, which has been pioneering this field, usually on the low mass end. But now with all of these multi-wavelengths measurements and all of those missions, we should be able to actually map out the distribution of most of the baryons, detailed profiling, as well as stars, and the dark matter through gravitational lensing. So with those, I think we are in sort of the golden era of being able to actually then think about how to do precision cosmology using nonlinear structures, as well as galaxy formation at the same time. With those surveys, I think we are facing one of the cosmological tension known as SA tension, analogous to H0 tension, has been one of the main issues that is at the crossroad of cosmology and astrophysics. It's a tension between CMB measurements and growth of structure mapped out by galaxy clusters, cosmic shears, and many, many different probes. All of those probes seems to indicate that the S0, S8 value, which is a combination of sigma A and omega matter, which basically measures the clumpiness of the universe through the nonlinear scale structure in present day, is inconsistent with CMB. This is a tension that we had been facing. I think there's a question as to whether the tension is due to cosmological new physics that would be exciting, or this is actually due to some unknown galaxy formation physics. The latest updates, I think, from the cosmology conference a couple weeks ago is that SA tension does not exist in cluster cosmology, with the latest measurement from SZ selected survey with the lensing mass calibration that is not bias affected by the hydrostatic mass bias, does not see SA tension. That has been resolved, and in fact those measurements are now being used to actually put upper limit on neutrino mass. So they're pushing away with the cosmology. The effect on the cosmic shear is more severe because it's difficult to mitigate. Most of the structure that you're seeing is galaxy groups, and the 14 solar masses object, and those are much more susceptible to baryonic feedback. The different simulation indicates that the baryonic effect on the matter power spectrum, which needs to be accurate at the level of 1% in order to realize the statistical power of Euclid and Raman, their baryonic effect can have 30% biases, which needs to be pinned down at the level of a few percent over the next few years if you were to actually do cosmology as promised. Recent measurements from weak lensing and KSZ is actually providing very detailed insights into the effects of baryonic effect, and in fact indicating that there's a significant lifting of gas, perhaps even more than what has been predicted by some of the simulations. So galaxy clusters ready to go for cosmology, galaxy groups or cosmic shear, they are very sensitive probe of baryonic feedback. Even for galaxy clusters, there is a systematic floor. We don't understand ICM physics perfectly, so there is a floor, and one of the key systematic uncertainties are in the scatter in gas profile at any given mass, and which affects the selection function. This is the big uncertainty in our ability to push even galaxy cluster cosmology in the future, so I'd like to say a few words about that. In addition to identifying individual galaxy clusters and groups to do those measurements, one can also do field level inference by, after removing those objects, you can compute things like power spectrum, as people did in the CMB primary power spectrum, and that contains a lot of information about both cosmology and astrophysics. You can do this using CMB map, which contains thermal kinetic SZ effect, thermal and kinetic SZ effect, as well as CMB lensing. You can do that analysis also analogously to the X-ray Rosita maps, and you can gain constraints on both cosmology and astrophysics. There are many multiple ways of actually gain cosmological and astrophysical signal. Just one slide on what we have learned from simulating galaxy clusters. And there are actually two regimes. One, in the inner region, 20% of virial radius is dominated by baryonic feedback due to AGN and supernova, while outskirts of galaxy cluster is actually less, they're not significantly perturbed by AGN. In fact, the physics of galaxy clusters outskirts is quite different. They are dominated by non-thermal pressure, which increases the function of radius. The shapes of dark matter halos, splashback rays, we see the outer boundary of dark matter halo. The accretion shock radius is actually located a factor of 2 larger, which is an interesting phenomena, as well as there's a plasma physical effect. For example, the electron-proton equilibration time is longer than the age of the universe, so that could actually cause steepening in thermal electron density profile, thermal SZ profile in the outskirts of galaxy clusters. Point of all of this is that all of these phenomena depends not only on mass, but also the mass accretion rate. They give a rise to scatter in galaxy cluster. For example, non-thermal pressure, if you split based on mass accretion rate of the halo, the early forming halo have a much suppressed non-thermal pressure. More recently accreting halo is has driven the significant gas motion, so non-thermal pressure is significantly larger. On the mass temperature relation, for example, the late forming, less recently forming halo tends to actually go below the average mass temperature relation because most of the energies are still in the kinetic form. They eventually dissipate and heat the gas, so temperature goes up as an evolutionary track from the bottom of this curve, of this line, to the top of this line, and they become much more spherical after their virialization process. So these scatters have a significant amount of astrophysics, and which is driven primarily by mass accretion rate in the outskirts of galaxy clusters. Now, with those in mind, we actually want to then write down what's the simplest model we can ever write down. And one can turn to something like a polytropic model developed by Jerry Ostreicher, and asking a question, what are sort of some of the simplest things we could do to actually capture all of those things that we have learned. We write down, for example, there's something similar to stellar structure, Lane-Emlin equation, but we have to make a modification that there's a dark matter halo. So we put the gas in equilibrium, hydrostatic equilibrium with the dark matter halo, given by an FW profile, for example. We take into account that the total pressure comes from the sum of the thermal and non-thermal pressure, and they follow the polytrope. We have to account for the fact that the inner cooling and cooling region, the equation of state, could be affected when there's a strong cooling and heating. We, of course, have to account for the fact that some of the baryons turn into stars, so stellar mass-halo mass relation, the slope is somewhat uncertain. This is you can write down one parameter model feedback, which is a combination of AGN and supernova, which captures the trend that when you inject heat according to some fraction of the rest mass energy of the stars, inject into heat, it puffs up the gas, heats the gas. So that's one way, simplest way of actually modeling the impact of feedback, where efficiency factor captures sort of the strength of the AGN feedback, and of course, importantly, the non-thermal pressure, which increases with radius, needs to be taken into account. And that there's an outer boundary of the pressure, which we also need to define. This is a 2 times our splashback radius, shock radius is located much larger. And there are some uncertain parameters which can be which still need to be determined, and some of the efficiency factor of AGN feedback, for example, is left as a free parameter. So this is the simple model, and once you write down this gas halo model, one can then predict for example, the map level SZ power spectrum, how much thermal SZ power you expect as a function of large scale to small scale. And then you can vary the effect of AGN feedback, the feedback processes. If you inject the feedback, it puffs up the gas, lowers the SZ power, and then move the power from small scale to large scale because the gas is puffed up due to the feedback processes. Most importantly, the non-thermal pressure. Those are driven by the mass accretion history. If you do not include non-thermal pressure, the thermal SZ power is overestimated by 60%. It's a big effect. It needs to be modeled to the accuracy. So you can use, once you do those modeling, you can use, for example, the Planck SZ measurement, power spectrum measurements to actually then constrain the effect of feedback on small scale, the effect of non-thermal pressure and cosmology on large scale. So these are the kinds of of modeling that we could do to understand the gas halo connection. One can also use the exquisite measurement from Chandra observation of SZ selected cluster from my McDonald et al. Here, and the error bar is so tiny for the X-ray measurements that it provides very strong constraints on some of the feedback, on some of the gas model parameters. In fact, we didn't include the Kuko model in the past, and which led us to actually introduce this Kuko model in the center in the form of the changes in equation of state. Once you include that parameter, you can explain the radial distribution of gas, hot gas, from redshift of 0 out to redshift of 1.5. One can also use the gas mass measurements from galaxy group 10 to 13 to 10 to 15 solar masses, which sets the overall normalization of the gas fraction in our universe. So once we have that calibrated model to the observation, one can use those to paint the n-body simulation using Halo catalog, for example, from the universe machine, Uchu simulations, a 2 gigaparsec box simulation at a given halo masses. We then paint those spherical gas profiles, and you can create half-sky light cone simulations. The same simulation has been painted, the galaxies has been painted using universe machine, which then reproduces the clustering and also stellar mass, halo mass revolution out to redshift of 7. So once we have this model, then we can actually now look at the X-ray sky as a function of feedback parameter or any other parameter that's in that model. This is just an illustration of how increasing feedback changes the log n, log s, the number counts of the X-ray galaxy clusters. So this is a very useful pipeline for us to then characterize the selection function, how that's affected by all of the physics that I talked about. One of the important things is actually the scatter. We so far just modeled the medium profile, but there's a scatter in, for example, in pressure and density profile at a level of about 10 to 20%. Usually it's the inner region, the scattered inner regions are driven a lot mostly by the AGN feedback in those massive cluster simulations. Outskirts are driven by those non-thermal pressure, which depends on mass accretion history. These scatters are important because when you compute the power spectrum in X-ray or SZ or cross-power spectrum, if there's a fluctuation from halo to halo, that creates additional power in those measurements. So if you don't include scatter, it leads to biases in those in the X-ray or SZ or power spectra at the level of 10 to 40%. Very important effect that we need to take into account. The scatter is extremely important. The other thing that we need to take into account is to go beyond the spherical Cal approximation. The halo is known to be triaxial, and that if you're looking through the halo along the long axis, then you expect the X-ray luminosity to be boosted. So there's this orientation bias that also needs to be taken into account in addition to intrinsic scatter of the halo. We call this extrinsic scatter, and really the combination of those two actually then determine the observed scatter that we see, and that affects your selection function. So we're actually doing, through this mechanism, we can then the forward model all of those selection bias effect, for example, in X-ray, doing the same in SZ. One effect that we notice is that one can then do the halo-based pasting by painting the spherical halo, and you can create a TSZ map that looks something like this. One can do something a little bit more sophisticated by painting that halo according, the gas according to the dark matter particle, which contains the triaxial information, halo information. So you can see that the SZ signal is somewhat distorted because it's following the underlying dark matter structure. So you can make that the TSZ model a little bit more realistic by pasting based on particle-based pasting as opposed to halo-based pasting, which only uses the halo position information. However, doing particle-based pasting is order of magnitude more expensive. The reason why we did this is that for a KSZ effect, if you do halo-based pasting at every location of the halo, you see positive and negative signal because KSZ effect is sensitive to the peculiar velocity, which could be positive or negative. So at the location of each halo, you see positive and negative signal. But when you do the particle-based pasting, or pasting also onto the dark matter distribution beyond the halo, you can see the KSZ map is very different, indicating that this is actually getting significant contribution from IGM. And so the modeling IGM, especially for kinematic SZ effect and also FRB, which gets most of the contribution from the IGM, is particularly important. We're developing a model extending beyond halo model to include effective filaments. Maybe another direction that we are going to is to actually go in lower masses in CGM, which we heard a little bit about. We're collaborating with the CAMELS collaboration at the Center CCA, and we have used those simulations to actually study how CGM property actually looks like and how we can use those to interpret some of the recent multi-wavelength observations. This is the simulations of those 4 simulations of one of the 25 megaparsec box from illustrious TNG, SIMBA, Astrid, and Magneticum. Blue is gas density, red is temperature. All of those simulations are designed to reproduce stellar mass, halo mass relation, black hole mass relation at redshift of 0. But if you look at the properties of CGM and IGM, because the implementation of baryonic feedback is quite different in those simulations, that you can actually see the very different properties of CGM and IGM, especially in SIMBA. The feedback is so ejective that it actually blows out the gas and actually makes the universe a lot more homogeneous. So if you have a fast radio burst through many of these sight lines, you will see much more homogeneous universe compared, for example, to illustrious TNG, where you might not see as much dispersion measure over here. You see a lot more, so you expect to see more scatter in this thing called McCord relation, dark dispersion measure redshift relation that the Zhao talked about earlier today. So nice thing about CAMEL is that you can model the observable X-ray map as well as distributions of galaxy as a function of cosmology, supernova energy, AGN feedback, and so forth. So that gives us a way of sort of exploring the impact of the of cosmology and galaxy astrophysics on X-ray observations. I will mention that there's the recent detection of stacking measurement from Eurosita, which detected the X-ray surface brightness out to larger radii. The measurements are so exquisite that you can actually test some of the latest cosmological simulation models, and in fact using CAMEL simulation, because it explores fairly broad parameter space in cosmology and astrophysics, we can always find the model that reproduces the X-ray surface brightness profile. But interesting question to ask is that for the best fit model that is reproducing the Eurosita CGM measurement, it turns out that it's very difficult to actually reproduce. None of the model that we've looked at so far can reproduce stellar mass, halo mass relation in the present day universe. This is interesting because that it indicates either that any of the feedback model, the galaxy formation model we have looked at, is not capable of reproducing both of those measurements, or it could be indicating that the X-ray measurement is biased. In fact, there are multiple reasons that X-ray stacking measurement could be very challenging, and these are some of the reasons that we can talk about. Good news is that you can do similar analysis on stacked TSZ effect. These are stacked measurement from Act and Planck, stacking on 600,000 galaxies and measuring the same thermal gas. And when you do the same similar analysis on the stacked SZ measurement, there's a slightly less tension. So maybe that this raises an interesting question. Maybe some of the tension that we've seen with X-ray stack is maybe reduced. Maybe there is an evidence of thermalized CGM, and we might even put constraints on cosmic ray origin of the X-ray signal through inverse Compton that Phil Hopkins talked about a few days ago. Maybe I'll just skip here, and maybe I'll end with this note on the impact of baryons on matter power spectrum. One of the good news is that this thing called baryon spread, how gas is displaced from the original dark matter location, which you can measure in hydro simulation. And this is all due to feedback. This is a net effect of how gas has been moved, regardless of what is driving those gas motion. And if you measure the baryon spread, and so it's a study the impact of baryons on the matter power spectrum as a function of baryon spread, there is a very good correlation. So that if you could measure the baryon spread, then we should be actually be able to actually correct for this baryonic effect or model the baryonic effect. Of course, the baryon spread is measurable in simulation. It's not much observable. But we found in recent work by Isa Medlock, who talked about earlier on her different work, that there is a very interesting correlation between baryon spread, how much gas is is puffed up due to the collective feedback effect from supernova and AGN. In fact, that this quantity actually correlates very strongly with the FRB observable, known as an F parameter. This is a dispersion and dispersion redshift relation, and in fact, this relation seems to hold rather universally for a wide range of cosmology and astrophysics. So in principle, that this matter power spectrum is calibratable, similar to supernova type 1a cosmology, where the supernova type 1a is not a standard candle, it's a standardizable candle. Matter power spectrum is a similar way. If you can measure the F parameter, the dispersion in the FRB skies, then we should be able to actually infer how much baryon puffing that has occurred in our own universe. So this opens up a possibility of actually using those baryonic feedback measurements from FRB then to do the precision cosmology in the future. So maybe I'll stop here. Thank you.
Actually, if I could ask the next speaker to come down and start getting set up, and then a quick question from Viraj at the back.
Thanks, Daisuke. That was beautiful stuff. You mentioned early on for your halo gas model that you have 5 astrophysical parameters encoding things about the structure of your CGM and your model, star formation feedback. Do you set priors for these parameters, and do you infer degeneracies between them?
We don't set any sort of priors. We explore fairly broad range. There are a number of, we can maybe discuss a little bit more in details, but yes, there are degeneracy, and we have to account for those degeneracy when we allow the parameter to be varied.
Yeah, I can see a quick question, but if Wada wants to just come and start plugging in while we, yeah.
Hi, super interesting stuff. Can I quickly ask you, so one of the things that comes to mind when you show all these differences in baryonic feedback effects is when we use AGM feedback, we're limiting ourselves generally to thermal feedback. Have you thought about what could be the impact of including cosmic rays, radiation, all these other physics that typically are missing in these models?
Thermal simulation, we have so far looked at in thermal and single features that are implemented in each model. There are in the slide that I skipped by Isa, who's here in the audience. She studied how there's actually an interesting coupling between supernova and AGN feedback, which are different in different subject physics. So it's a very rich physics on baryon cycle that we are discovering when we do these comparison projects on different types of subject physics. It's something that we can discuss